Oh, let's see. File, save. Ah.
Yeah, I think I have audio of the two first recordings if you want.
Pardon?
I can check later. I think I have audio of the first two talks.
Oh, great.
So
Oh, so we could, yeah, no, that would be good. So we might be able to patch that in. That would be really cool. If you could give them to Javier, that would be brilliant. So I'm just working out how to save as from this bizarre read. Oh, there we go.
but just open the slides here, follow up and record. Too keen. What? Too keen. Yeah, but then you can summarize. It's a big detector. Yeah, but I don't have all of them because there was one talk that there was no slides. So I was like, there's no point for me to record over the slides. Because I annotate stuff over the slides and get to see it. So I only have two.
But the one without slides, we might have the audio for. I think we switched it on. We realized it was good to switch it on later. Okay, so we've got today we're going to start by talking about Nicolas did a great job of reviewing different types of covariance, and there were lots of questions about how we get the parameters. So I'm going to start by sort of reviewing how we do that by maximum likelihood. We won't talk much about some of the sampling approaches we talked about. I'll also sort of try and emphasize this point about parametric models being a bottleneck. And if I've got time, I'm going to move on to the Kalman filter and multi-output sort of Gaussian processes. So we didn't actually go through this, but going from a parametric to a non-parametric framework, that was at the end of the slides. It was a thing I sort of briefly talked about on the board because we ran out of time. But the interesting thing about a Gaussian process is it's non-parametric. Now, people say non-parametric, and after a while I've argued with them for a bit, I realized they mean something slightly different from what I do. So what we're saying, and what certainly a lot of people will say as non-parametric, is that you can't represent the, within the model, you don't represent the information from your training data within a fixed number of parameters. That as the amount of training data increases, you effectively have to increase the number of parameters in order to represent that. So another way of saying that is actually you have to memorize the data. So in a Bayesian model, if it's parametric, we can normally decompose it in this form. Sorry, there's an additional bracket there. Ignore that bracket. The prediction over y star, so y star is now some corrupted version of f star, so it's related to f by a likelihood. Given where that's the test data, given the training inputs, the training target, sorry, the test inputs, the training targets, and the training inputs, is normally given by this expectation, the probability over the parameters y given the training data, the posterior distribution, multiplied by the likelihood, and then integrate out w. So that's normally how you write that sort of thing. We haven't really written that for a Gaussian process because you can't write it in that form. This implies that the model can be constructed in such a way that there's a set of parameters through which you're passing all the information from your training to test data. So I can't stand to think of that as a bottleneck for information about the training set to pass to the test set. The problem with this type of model is that you were deciding at design time how many parameters you want. So that might be good if you know how much training data you're going to get and you're never going to get any more training data. But in any sort of streaming scenario where you don't know where your training data is, that could certainly be a bad idea, because what will happen is you get more and more training data. So as you sort of gain more information about the people on your social network or whatever, you'll become more and more confident about what these parameters W will be. And in fact, under certain conditions, W just becomes a delta function. Regardless of what y is, W will just become a delta function. And that means that you sort of lose all uncertainty. So you actually lose the ability to pass new information from your training data to your test data. Now for me, this is the major reason why you use nonparametrics. You use nonparametrics because you get away from this type of structure. You can't write down. This is the thing you want. I mean, ignore the x stars and the x. This is what machine learning is to me. Probability of y star, the training data, given y, your test data. The conditioning on x is just the conditioning on what the input variables were. So, but the thing you're actually modeling is y star given y. And this is just a convenient decomposition that we can use in a parametric model. And we typically assume something IID for this likelihood, and then we assume a prior and obtain the posterior. So that's the standard Bayesian way. But, you know, to my mind, it's actually, what's the right word? Philosophically broken. Certainly for a learning system that acquires more and more information. All you can do is choose W to be absolutely massive. You have to do that, you know, in order to ensure that, like, so if we're born, then we have to have a W that's so enormous that throughout our entire lives we don't, you know, ever get a delta function on it, which is maybe what we do. I don't know, but you know, nonparametrics certainly as a conceptual, philosophically, nonparametrics doesn't suffer from that problem. Of course, it suffers from other problems that the memory has to go up with the data. So every time you see a new data, you effectively have to memorize the data. So that gives us other practical problems. But it doesn't suffer from this sort of what I call the sort of the bottleneck between the training and the test data. So because the problem is, how many parameters do you need? If the vector W is size m, how many parameters do you need at design time before you see your data? Now, nonparametric says, well, m sort of goes to infinity, that you can't represent it in this sort of form. So I think that's a powerful. So these degenerate covariances we talked about can be written in this form, but in general, a Gaussian process covariance like the RBF can't be written in this form. A degenerate one would be one based on basis functions. Okay. So this is the sort of degenerate covariance matrix that arises from a basis function model where these are the bases. This was the bit we didn't have time to go through at the end of my talk. But there's versions of me going through it in other talks. Okay. So that was the sort of point there. And I think these things are all stuff that Nicola went through. There are a couple of covariance functions that he didn't go through. So I like this one. This is a sort of the neural network covariance. And this comes from a paper from Chris Williams in 1997, I think, where he sort of asked the question. So you can show that you get this RBF or squared exponential or exponentiated quadratic covariance by seeing what happens if you cover your line with basis functions from minus infinity to infinity, infinite basis functions. In fact, cover your line or your space. And that you can show that the effect of weighting these sums up, scaling down the sort of weights on these things as you scale the number of basis functions up, gives you the Gaussian process with this sort of exponentiated quadratic covariance function. So you can show that that's what it leads to in the limit as you get infinite basis functions. Chris Williams then said, well, in neural networks, which was still, they were still kind of popular at that time in 1997, and then they sort of faded from popularity, but I've heard in some areas they're quite successful again. So Chris Williams, in those days, this was the sort of activation function of a neural network, but Chris used the ERF function for tractability. So normally people use tan H in those days. Nowadays they use some rectified linear. And you can do the same thing with this rectified linear. He showed that if you do the same trick, you lay out lots of these S-shaped, but some of them are the other way around. So you have prior parameters on where they sit and how sharp they are. So some are sharp and some are smooth. And you sum all of those up together. This is the covariance function you get. And you're seeing samples from it here. Now, the parameters of this, B, is a parameter saying where the offset of those basis functions are. So it's basically saying how far away from, the variance of the offset. It's the prior parameter over the variance of the offset. So it's saying how far away from the origin these little s's are. So what you'll see is that it's tending to saturate as it goes out here, because in this case the s's are constrained to sit near the origin. So as you move out into this side, you don't get any activity because you're just summing up a load of constant functions. Same on the right, on the left. The W parameter controls so inside the sigmoid, it's not actually a sigmoid, but conceptually inside the sigmoid, you've got something like Wx plus B. So the W parameter is the variance. It's a bit misleading. It's the variance of the distribution over the W's, and the B parameter is the variance of the distribution over the B's. So the larger B here, the larger the values, typical values you get of B, and the wider this area of activity moves out. And you can actually take B very close to infinity and you get something that looks somewhat stationary. The W parameter is telling you sort of how sharp the sigmoid is. So what the distribution of sharpnesses are, and obviously sometimes it goes negative and flips the sigmoid round the other way. So that actually gives you something. This thing is infinitely differentiable actually, but as you will, it's not really roughness because it's infinitely differentiable. You definitely see properties of the function changing as you change W up. As you take W to infinity, you've basically got a sum of sort of non-differentiable functions, step functions. But that's in the limit. As you approach the limit, it's infinitely differentiable. So it's a interesting covariance function that Chris derived in '97, more from a theoretical interest perspective, but it actually works okay in practice as well. It's not that widely used. So the linear covariance function is just that, and it will give you linear functions. And Nicolas talked a great deal yesterday, very eloquently, about how these sort of things can be combined to give you something that you're interested in. And another thing you can, for example, do, actually one thing I've tried once, but I didn't really find an excuse to put it in practice, is set B to 0. If you set B to 0, you get sort of interesting point symmetric functions in here. Nicolas has ways of doing that in general to covariance functions, but you get, if you set B to 0, exactly the effect that should happen happens, is that all the location parameters of these sigmoids are 0, and therefore you only see activity around this region here. Everything's symmetric around that region there because the basis functions are symmetric. So you can try that in the code. Okay, so how are these things used in practice? Well, you've played a bit. It's a shame Jeremy Oakley isn't here. So Jeremy Oakley was a PhD student of Tony O'Hagan. He was going to give the second introduction to GPs. They've used Gaussian processes for a long time. Tony O'Hagan wrote a paper on GPs in statistics in 1978. And the main thing that goes on in statistics is using Gaussian processes as emulators for computer code outputs. We've got Rich Wilkinson speaking perhaps a little bit about this later on. He's not here at the moment. Where you might have some computer simulation, slow computer simulation, e.g. predicting the atmospheric level of carbon, and you want to run this simulation more rapidly, so they fit Gaussian processes to the outputs of that simulation. Now in this case, the reason I use this example first, there's no noise because it's a computer. You're trying to recreate what the computer says. So there's no noise inside the computer system. So you actually interpolate exactly on what the computer says. So in other words, for the inputs, so the inputs here are like your initial conditions on the computer, like how much, how many power plants there are or something like that, or what the temperature is, I don't know, whatever they put in. And the outputs are the atmospheric level of carbon at a certain time. They also do this for climate models as well. Rich does this with climate modeling. But you want to know that your model produces exactly the same thing as the computer does for the values the computer produces them. But you're trying to build a surface so that you don't have to do every possible setting. So every time you want to know an answer, it takes like a day or 2 days to run your model. So you replace the model with the Gaussian process emulator, and you do a design such that you have observations of what the climate model is putting out at different points. So this is sort of a GP being used in that style of scenario where I've got 2 points and it's just going bang on through the point because there's no noise. So there's no noise process in this like there was in the models you were fitting yesterday. So this is an additional sample which happened to be right close to the mean. Extra samples like this. Now, the interesting thing, when I add samples in those intervening points to try and reduce the uncertainty there, the actual entire posterior collapses. Collapses to something that looks like it might be a delta function. We know it isn't because numerically it can't. Numerically it is, but theoretically it can't be. But in effect, numerically it is. And it's this covariance function I'm using here. This is the effect that Nicolas mentioned as to why sometimes, certainly in 1D, it's not a good idea to use the exponential quadratic. As points get closer and closer together relative to the length scale, because you believe in infinite differentiability of the function, you believe in a great deal of smoothness. So you basically collapse down to very high confidence about what's going on. Now there's some ways you can, so there's something called Berkner's theorem, which says that you can get any stationary covariance by thinking of it as a filter in Fourier space. Nicolas mentioned this in the context of Andrew Wilson's work, where he was constructing these filters in Fourier space. So the filter in Fourier space, I mean, making it symmetric, but for this covariance function is a Gaussian. Yeah? Now, when you see this, you should immediately start thinking, this reminds me of something. What does this type of effect remind you of? Being able to completely recover a signal from uniform sample? Yeah, so, and what's the name of there's a theorem that says that you can recover signals. Yeah, I think it's the Nyquist one, isn't it? Nyquist sampling theorem, yeah. Now, what Nyquist sampling theorem tells you to do is that if you've got a low band pass filter, in effect, if you know your signal has no frequencies above a certain point, you just have to sample at double the rate of that filter and you will recover the underlying signal exactly. You don't have such proofs for this covariance because it's got support for all frequencies all the way up to the top. So in theory, anything can happen. This is why this model's a universal approximator. In practice, don't try it. It's not a good, this is the difference between theory and practice. You know, actually, I think it was Philip who has some really nice examples in his intro to GPs about what happens if you use the wrong sort of covariance function and start trying to fit. In theory, you can fit any function with it, right? But if the parameters are wrong, you will do some really stupid things on the way to fitting that, and you only really fit it in the limit of infinite data. So you know that these covariance functions are universal approximators in that way. They can fit any function, but when that comes into play is way too late. You want to get the properties of this function right. So what goes on with the RBF is it's dropping quite rapidly towards 0. So it exhibits some of these characteristics of this low band pass filter. You know, it sort of doesn't really believe in high frequencies. It filters them out. So it sort of says, in this case, it's saying, I don't really believe anything high frequency happened here. It might have done, but I'm dropping to 0 so quickly, exponentiated negative quadratic, that I'm squashing it. And so the posterior is very like a delta function. It's not quite a delta function. In the case of this, you can build the covariance function based around this, and that will collapse to a delta function. That's somehow degenerate on these frequencies. And the whole of signal processing is kind of based around that idea. But it's a pretty crappy idea, because that's a pretty crappy assumption for your functions, certainly from a machine learning perspective. So, and in practice, what they tend to do more and more is they sample at massive rates, and they assume the frequencies that go through are really, really high. So I don't know. I think it's interesting to relate that to how we think about things in Gaussian processes. The type of covariance function that Nicolas talked about to use as defaults use, instead of a Gaussian here, they use student T style filters. So a student T, I can't remember its formula, but it's heavier tailed. It has a degrees of freedom parameter, and that degrees of freedom parameter turns out to map to this Matern 3/2 type parameter in some way I can't remember. So the student T has heavy tails, so it allows higher frequencies. So you can, with these student T filters, you get non-differentiable functions at one limit, and you can vary the differentiability. As you take that degrees of freedom parameter towards infinity, the student T becomes the Gaussian, so the RBF is itself within that class of Matern, as is that exponential covariance. They're all within this class of covariance functions, and they're specifying different amounts of differentiability. If you want to read more about this, the reference on this is Michael Stein's book on, I can't remember what it's called. It's some theory for Kriging. I can't remember the first. Spatial, I can't remember. The subtitle is Some Theory for Kriging. And he'll talk quite a lot about that in there. It's quite a technical text, though. So, of course, in practice, this problem doesn't occur quite so much in terms of collapsing to a delta function, because normally we have a noise. And even in this scenario where they're trying to emulate the outputs, they often introduce the so-called nugget term, as it was called the other day, which isn't a noise they believe in. They introduce a little bit of noise to try and make things more numerically stable. In this region here, this is very numerically unstable, because the posterior is collapsing to this sort of delta function-like object. So in practice, they tend to introduce noise. And we also talked about introducing noise yesterday. So we can see noise models as this. And Alan's going to talk about sort of how we can take these models and turn them into non-Gaussian. But in general, we think of a noise model in a Gaussian process as relating our observation to our latent function f. So we normally think of the function f as latent. The Bacco example is an unusual example where we observe the latent function. And this is, in the standard case, if we say it's Gaussian distributed with a mean of fi and then corrupted with variance of sigma squared, this just gives us this additional covariance function where this thing here is the Kronecker delta. So it says basically, look, if the indexes of these are the same, put in a sigma squared. Add it, so i.e. along the diagonal there's a sigma squared. Sometimes you'll see this written as the Dirac delta. If things are operating over time, the Dirac delta kind of makes sense. I think the Kronecker delta makes more sense in general, though, because it's really on the index. It's like if the observation is the same on the index I, then you expect additional noise to be added because you don't expect when you put in at the same location. So if xj is the same location, but a different time that you made the observation, if you're revisiting that location, so different index but same value for x, you don't add this noise because it's not correlated then. It's things that aren't correlated. It's something sort of totally independent of the spatial location. It's dependent on the index. That's how I'm writing it here. You could do it the other way. So for example, if you took the limit of this RBF covariance function as the length scale, which is missing here, goes to 0, then you would recover a different type of delta function, right? You would recover something that says spatially I always see noise there. So it's a slightly different conceptual thing. So I think of it this way, but that's a sort of subtle point. And we just add this to additional covariance functions, or we actually include it in a noise model, which is what's done in GPy. So this is regression now. So instead of observing the function itself, we observe a corruption of the function. And whereas before what we saw was the mean was going directly through the function and that the variance collapsed around that point, now what we're seeing is the mean doesn't necessarily go towards the function. Because the prior is sort of pulling it back towards 0, there's some sort of pulling down effect here that's saying, no, well, that's an extreme versus where I expect you to be. So I'm slightly biased towards 0. And the variance at this point is like the variance of the process, the underlying process. And as we add more data, we can sort of get a better estimation of what the underlying function is and get a tube that is, so we're seeing, because of smoothness, we're seeing a tube that is approximately the width of our underlying variance. And as we leave the data, then the variance goes up because we're uncertain about where the function is going. Okay. So what you'll hear about in a bit is how we do general noise models in these processes. So how do we do things that are non-Gaussian or things that are discrete observations or whatever? The typical trick is the same as the typical trick is to make fi a function that's in the likelihood, a parameter of the likelihood. So fi can sometimes be a log rate. So in a Poisson count model, you might say e to the fi is the rate of disease or something like that. And doing this is known as generalized linear models. And what we do in Gaussian processes that Alan will talk about later is we have to actually, one trick we can use, you can either go to sampling to fit these models where things are non-Gaussian, or you can approximate each likelihood, each site with a Gaussian likelihood. And this is the approach that's taken in sort of GPy. So you end up taking what your real likelihood is and approximating it with a likelihood that looks Gaussian, and then you do your inference a little bit as before. So that idea that Alan will talk about later is depicted briefly here. So we've got a prior that's coming from our latent function. So this is the prior for a given test point over f star. Now let's say we make an observation of what the real value of that test point is. So if it's a classification problem, this is the sort of observation we make. We say, well, this is a latent function going into a probit likelihood. So I've got that on the previous slide. So we say that the probability of our observation is given by two curves. So if the latent function's coming in here, the probability of it being 1 is this blue curve here. So as fi goes positive, the probability of the observation is more and more likely to be 1. And as fi goes negative, it's more and more likely to be 0, or minus 1 as we put here. And this is the corresponding probability distribution for yi, cumulative probability distribution, as a function of fi. So in this is a way we can construct a likelihood to sort of fit in here. These are sometimes called squashing functions in machine learning. In statistics, the function we're drawing here is actually the inverse link function. So in statistics, they tend to talk about link functions, and they don't tend to talk about the function in this term. They tend to talk about its inverse, and they talk about this would be the inverse link function. So the problem is, once you sort of combine this prior of where you thought the process with this likelihood through Bayes' rule, you get a posterior which is non-Gaussian. And the trick generally is to try and approximate that posterior with something that's Gaussian, to project back into the Gaussian process world. So all approximations will do that, but Alan will discuss more about that. So questions at that point before I move on to fitting covariance parameters?
Yes, why wouldn't you use sampling in this situation? Is it because it's too computationally heavy, or is it other problems with using?
I think you can use sampling. James Hensman has a nice NIPS paper showing ways of doing sampling, new ways of doing sampling. There can be problems. The sort of thing that paper addresses and other papers try and address with standard sampling methods is you need to do sampling. You want to do sampling over f and simultaneously over the parameters of the covariance function, and that can be a bit ugly. Maurizio Filipponi had an approach where I think, I can't remember the details, but they used approximations like this, I think, within the sampling algorithm to sort of take samples that were known to be good, but I can't remember the details of how they did that. So the challenge can be that in the Bayesian model, you've got hyperparameters over your covariance function, and then you've got the latent function. The latent function has a lot of sort of particular characteristics. We also had a paper with Michalis Tsitsias some years back where we had another approach to sampling latent functions, because the latent functions are very correlated a posteriori. So you just have to be a bit careful. If you use something naive like Gibbs sampling, it doesn't work very well. I'm not an expert on sampling, but these are the things that you hear on the grapevine. So you can, and if you have small data, I'll tell you what as well, I think Michael Betancourt's STAN software allows you to specify, I've not done it, Gaussian process models and ask it to sample stuff. And that would be using their standard probabilistic programming sampling techniques they're using. So I think that's an interesting thing to try. My suspicion is, in general, it's generalization for very large data, it becomes prohibitively slow. But that might be wrong, and we might see sampling methods like James is coming through and dominating these other approaches. Okay, so forgetting sampling for the moment and going back to sort of how, without even putting priors over the hyperparameters, we can attempt to find those parameters. So this is the object we're actually trying to fit to our data. So as we notice, it's not like, as we normally expect in a likelihood, some kind of product over I equals 1 to n values of data points. It's this interesting thing, which is the Gaussian, multivariate Gaussian with zero mean if we've got no mean function, and it includes two terms where our covariance function is. So this is the covariance matrix computed according to this covariance function. So inside that covariance matrix are these parameters theta, and the input variables x, which in the GPLVM we treated as parameters. Incoming call. Yes. 0843. I think that's someone telling me I've got payment protection insurance. So y transpose k inverse y and k. That's where these two, where k appears. So I'm highlighting those in blue and red because these are sort of the two terms that we're interested in. And they were sort of mentioned a little bit yesterday. So in particular, the log determinant term actually turns out to act as a bit like a capacity term. And someone mentioned this idea that the Gaussian process covariance, is covering, you mentioned, a certain number of functions, a certain space, and that perhaps we want to cover as many as possible. So that's what's really being measured by this term here. It turns out to also be the entropy of the Gaussian process. And I'll try and give you an intuition about how to think about that term and what this coverage means. This term here, rather oddly, if you're used to kernel methods, this is a bit freaky for you. This is a data fit term, not a regularizer term. In kernel methods, this is something that looks like this is seen as a regularizer term, but it's not this. It's actually F transpose K inverse F, where you're trying to, in kernel methods, optimize over F, the latent function. So the key difference in a kernel method and the Gaussian process is we're integrating out over F, whereas they're trying to optimize for F. So it's like a map optimization would be our perspective. It's similar to that. So the thing that looks like a regularizer in their case is not it's the data fit for us. So that can be a little bit confusing if you're used to seeing those sort of derivations. So just to clarify that. So we've already talked about this decomposition of a covariance matrix, which I like. So that the covariance matrix in 2 dimensions has its eigenvalues, which are the principal axis of that ellipse. And R gives us a rotation away from that sort of axis-aligned principal axis. So the capacity control term is actually the determinant, which is the product of these eigenvalues. So this is not the actual eigenvalues, it's the square root of the eigenvalues, because I want to look at what these objects are, right? So these 2 eigenvalues like this are giving us this basis, and the product of the 2 eigenvalues is lambda 1 times lambda 2. Now, both my sons, who are 8 and 12, should know that that gives us the area of the square that the axes sit on. So that's giving us the area, and of course if we take a 3rd dimension, that's giving us a volume. So it's sort of giving us a volume that's sitting under the footprint of this GP, right? It's just that area. Apart from, it's not quite that, because, of course, these things could be negative in practice. There's no reason why they're not the squared. This is the squared eigenvalue. So these things here would be negative if they're pointing down here. So if you just take the product, you could get an area that's negative. So it makes sense that what you then do is you square that and you square root it. So the thing you're looking at is the determinant of the matrix, of the square of this matrix, then square rooted. Because remember, it's the determinant to the square root. So you're getting lambda squared determinant square rooted. But that's, in effect, just saying all these are constrained positive. It's still the area underlying the Gaussian ellipse. Of course, if we rotate it, that's still the same thing. So rotating gives us this slightly different basis. So now these bases are vector W1 and vector W2, the rotated original bases. And this is R lambda. This isn't the entire covariance, because the entire covariance would be this matrix W times W transpose. R lambda, lambda squared, R lambda, lambda, R transpose, or R lambda squared, R transpose. But that doesn't affect the volume. You still get the same volume out. So that term is ambivalent to sort of rotation. It's just measuring the sort of number of different functions which aren't countable, so over some sort of continuous space. So as Nicolas put it, it's a random process. Like every time you roll this dice, there's a function on the dice. Well, this object here is the number of sides that dice has, in some sense. It's a continuous sense, so somehow it's a round dice or something. But you know, we'll leave that to mathematicians. Now, this is the data fit term. So the data fit looks like this. Now, the way I tend to think about that is you've got something centered on 0, which is like a well, a quadratic well. This is a quadratic form, right? So this K, now instead of specifying the principal axis, instead of specifying the ellipse of a Gaussian, please think about it as the ellipse of a quadratic form. So it's just showing us sort of a contour of a well. So I've drawn 2 to show that this is higher than that. There's no way you can tell whether it's higher or lower, but that's what I'm telling you. At the 0, when y is 0, at this point here, this whole thing is 0. So there's a minima there, and as you go out, it goes up in this quadratic way. So when you've got a data observation, so now you need to encounter a y. So y is y1 and y2. So there's only 2 points being observed in this Gaussian process, because we can't plot anymore. This is point 1 and point 2. What we want to do is we want to get that as close to the center as possible. But we can't just blow up this well. We can't blow up, well, I mean, sorry, that's too many metaphors. Coming out in the wrong way. I've got an exploding well in my head. We can't just sort of expand the sort of slopes of this well. We can't just sort of say, okay, let's just scale down, or scale up k, therefore scaling down KL inverse, to bring this contour out. Because if we do that, then we pay a penalty. I mean, we can do that, but we pay a penalty here because this coverage increases. So it's sort of saying you can do that, but now you're explaining more functions, so you're in trouble. This isn't, of course, how any of this works out. It's just in the maths at the end, and it's an explanation that's useful if you're used to sort of frequentist explanations of capacity control. Now, but what you can do is something like this. You can do these sort of operations without penalty. So you can increase correlation between y1 and y2, if it's possible, within the parameters of your covariance matrix. You're not free to just rotate that, But if the corresponding x1 and x2 were close, and just by making, so initially maybe your length scale is small. So we could be in an initial situation where we've got y1 and y2, and this is what our mean function says. By the way, that's the mean function. Of course, the posterior will have all sorts of uncertainty around that. That's not what any sample would say, but the mean function might look like that because the length scale is very small. So some people call that overfit. I think it's a very poor term to use in the case of Gaussian processes because it's confusing what you mean by that. But people will call it overfit, so let's call it overfit. So the length scale is small, and basically we have independence between these 2 points. This isn't ideal because on my plot here, I've actually got this direction wider than this one. In this example, that wouldn't be the case. If it was an RBF, it would be a circular contour. Now, by increasing the length scale, we'll start getting functions like this, but we'll also get, in effect, correlations in our Gaussian process between those 2 points. We start to see terms in the off-diagonal popping up as we increase the length scale. And so this correlation now, in effect, mentally can cause a rotation here if these points are close. If those 2 points were distant and there was a load of crap in between, it wouldn't be able to perform that operation without screwing everything else up. It would have to correlate everything else. So, I mean, we're just thinking about one kernel very much and one example. So you can sort of see how you get this sort of trade-off between the sort of operations it can do. It can, in that case, it might have to blow things up, or typically, you would also have a white noise. So another thing, if you have that white noise term added, you sort of have a circle here, which you can expand and contract independently of this object here to capture things. So that's how your white noise term would operate in this, sort of blowing the thing fatter without changing the length scale. So this is what the GP somehow, I mean, it's not trying to do, I'm anthropomorphizing it here, but if I were, was it Ilya Sutskever at NIPS, if I said, that's what it wants to do when it learns, you know, that's what it's trying to do, that's what neural networks do, so GPs do the same thing. So this thing here is now what we're going to show is how these terms vary as we change the length scale. So I'm just going to change one parameter. I've set the variance to be correct. So this data is sampled from the GP. And I'm going to show you, as I increase the length scale, what happens to these 2 terms and what happens to our fit. So this is the situation I talked about there. I don't like to think it's so much, I mean, maybe you could call it overfit. But look, it doesn't really think the function goes through there. It just sort of says, all I can tell, it's saying I know nothing about what's going on, apart from the function is close to the data point in the region of the data point. Yeah? It's not, in that sense, it's not overfitting, because it's not saying, I'm sure the function goes through there. This concept doesn't really work for a Gaussian process. It's saying, I know nothing about what's going on, apart from, I think, right close to the data point, it's somewhere near the data point. But as soon as I move away from the data point, I become ambivalent again. I think it's between 0 and 1. So it is something that makes me a little bit cross when people call that overfitting, because it's being very ambivalent. But actually, this is the example where the function class at the beginning is as wide as possible. The reason it knows nothing about what's going on is because it believes in so many functions that when it sees the data, it says, well, yeah, but it could be anything, couldn't it? So this is the one which has the sort of best data fit, actually, which is why I guess people call it overfitting. But as I said, I don't really like that term. But it's got the worst capacity. And as we change the length scale, we see that changing. So we see that the data fit, this is minimizing, by the way. I'm not maximizing. I should have made that clear. This is an error function, so I'm taking the negative log likelihood. So up is bad and down is good. So we're seeing as we go up, we get functions where our concept of the number of possible functions within the space is decreasing, but the quality of the data fit is getting, worse, yeah. So we're considering less functions. So there's this Occam's razor effect that I can explain what I can explain with this class of functions I've allowed myself and the functions I'm actually explaining at the moment. So of course, this is just, I mean, this is a very involved explanation of something that's maximum likelihood with only a couple of parameters. So you might expect it to work, but it's sort of worth doing because a lot of people are surprised that you can learn kernel parameters in a Gaussian process. And here, this is a discrete minima, so the actual minima is not quite on this position here, but it's somewhere close. So this would be the minima. So this is the one it would select if we were testing discrete number of values by the likelihood. In practice, of course, we optimize. And this is the true value. But in practice, you wouldn't recover the true value. You'd recover something just to the left or the right of it because you're unlikely to recover the true value. So that's great. So this here, I think you would agree, is quite a nice fit. I mean, it's not the case that we know it's the best fit. If we, in some sense, this is maximum likelihood. What we should really be doing, look, there's quite a flat error surface around here. So we're reasonably insensitive around that minima to what the value of the minima is, which suggests that we don't have enough data to be confident of whether it's that or that. You know, maybe not that. See, that one's much worse. But that and that are about the same, aren't they, under our model? So really, even for this example here, we should probably be doing some form of sampling or this CCD thing that we mentioned that we're not going to talk about, but Aki Vatari does, to try and account for both these models as potential answers. So questions about that example, then I'll show you a real example where we get actually multimodality, because here this is unimodal, but then I'll show you an example where even for only a couple of parameters, you get multimodality in the fitting of these things. So questions about that? No? Good? All clear? Brilliant. So, the example we're going to look at is this thing I did with Freddie Kalaitsis, who was a PhD student of mine. And we're interested in gene expression, which Nikolai nearly mentioned briefly yesterday. The experiments he showed results from for gene expression. We do quite a lot of gene expression in Sheffield. But it's a gene expression time series. So gene expression is the amount of RNA you have in your cells being prepared to convert to protein. So it's a sort of it's a measure of which genes are switched on. And you can measure each cell individually. And we've got a time series, but sometimes it's quite noisy gene expression. So sometimes you might see something like this and you think that expression's changing, but you might get other expressions which are like this. And the question is that noise or is there an underlying function there? So this is the sort of thing a biologist wants to know. They want to know which of the gene expression time series I've measured are dominated by noise and which actually have some time series process to them. So Freddie and I sort of had this idea to what we could do is just fit a Gaussian process to each of these, and then we could look at the scale associated with the exponential quadratic, which is like the signal, and then we could compare it to the scale of the process associated with the noise. So there's delta ij sigma squared. And then we could sort of say, well, the ratio between these two is giving us a signal to noise ratio. And we can actually see if the process we're seeing is dominated by that or dominated by that. And then we can rank genes according to that signal to noise ratio, because biologists often want to sort of like filter their genes in some way. So the ones that are dominated by noise are sometimes called quiet genes because they're not responding to the time series. And the time series is generated by some kind of disturbance of the cell. So the biologist wants to know what's responding to the disturbance of the cell. So this is interesting. There's the paper, but this is interesting because we had sort of, I can't remember how many genes we tested, but thousands of genes. And then we were testing each one trying to fit for what these parameters were. And in order to make sure we didn't get caught in local minima, we were doing this particular thing. We were reparameterizing the covariance function to be a signal to noise ratio. So a ratio between this, and then we had an overall, we had an overall scale at the front. So I can't remember what we called it. Let's call it S for scale. So this parameter, if you do this reparameterization, you can fit this parameter by a fixed point update. So what we were doing is we were taking every point of plotting the log length scale and the signal to noise ratio, the ratio between these, and we were plotting the likelihood for that point. So we're not optimizing here. We're just sort of giving a MATLAB style contour plot. And we did this for 6,000 genes. It's quite quick because each experiment only contains 14 points. So things are very, very fast. It's always best to work with small data sets with Gaussian processes. And this example is, I think, the one, I don't know if there were another one, but I think out of the 6,000 or whatever, there was this one where it was multimodal. So it's not that common, even with 14 data points, to find these multimodalities. You can see the modes here. There's one there, and then there's one, it's actually more up here. But you can see the ridge forming up there. So this red is high. There's actually another solution you often find, which is down in this region here, that if you switch it all to noise, what's happening here, the reason the surface is distorting here is once you make the signal to noise ratio all noise, the length scale becomes unidentifiable because you switched off this term. So the reason for the shape at the bottom is that you're saying it's all noise. And there's typically, so you have to be a bit careful when you fit your Gaussian process. If you initialize with the wrong parameters, with the wrong length scale, you will fall into this region anyway. Even if it's not, I don't quite know if it's a mode or if it's just a big plane, you don't tend to escape this region. So you have to be a bit careful when setting that length scale. You have to make sure that you're not starting yourself off in a region where the length scale is saying everything's independent, because you end up falling down here. So what I'll show you is these different solutions. So this was length scale of 1.221 and signal to noise ratio of 2. So it's actually up here. Well, it's even up here, right? It's all the way up there. It's off the plot. And I'd say this does look more like an overfit. The length scale is like here, so it's sort of up there. So it's saying no noise, pretty much, and a very short length scale. Remember that likelihood, it's minus 0.22, the log likelihood. Compare it with this next fit, which is from this mode here. So this one's saying length scale of 1.51, so it's in there, and signal to noise ratio of 0.2, so somewhere around here. Oh, is it maybe in there? It's between these two. I guess we don't have the detail right there. It's somewhere in here. But look at the log likelihood. It's only slightly worse. So if you just weight these two models on the basis of log likelihood, these basically would be equally preferred. It wouldn't know which one of these things were true. So it's clearly a case where to get the right fit, you should be sampling. But there are also two modes. And you could fall into a mode that looks like that, or a mode that looks like that. And then there's another fit, which is, I think it doesn't escape from this if you initialize it with this. This is signal to noise ratio of minus 4.5, so it's down here somewhere. Length scale is kind of 2.9, but it's irrelevant. Once you're down here, it doesn't matter what your length scale is, and it's just saying it's noise. But for Freddie and I, we kind of didn't care in this case because we could see that those two options were both way more likely than it being noise. So for our purposes in this paper, it didn't matter whether it was that or that. I kind of doubt it's that. Very much doubt it's that. But, that one is also much more likely than that one. So we were able to sort of declare, okay, this one seems to be responding in some way to the time series. But just I like that example because it's quite hard to actually construct examples where you get this multimodality. But just we happen to have 6,000 ready-made real examples, and this one pops out.
Can I just ask about how exactly do you quantify the signal to noise ratio?
We just actually, all we do is it's the log ratio of the variance of this kernel to this kernel. So when you think about what they're saying, it works for stationary covariances. It doesn't make much sense for non-stationary, but marginally, you've got two covariances, and you're looking at the ratio of the diagonal elements, which are always constant for both these covariances. So you can sort of interpret that, the ratio of those two, as a signal to noise ratio.
So GP seems to be heavily reliant on your hyperparameter space and trying to find optimum. But given a set of data points, there are going to be more data points coming in. So do we have any kind of guarantees or anything about like the stability of the hyperparameter space? Because as we get more samples, more perturbations.
It's a good question, yeah. Yeah, no, that's a good question. I think that's a really important point. That updating hyperparameters as you gain data that's some sort of black art. It's I don't think people have really good techniques. So, yeah, the thing I was saying earlier about streaming data sort of assumes somehow that you know what your hyperparameters are. Yeah, I think that's a really interesting question, how you should update your hyperparameters as you get more data in. I don't know of good answers. I know there's theoretical answers that show, like Peter Solik has done a lot of work on learning curves to show, but I think that's for mismatched covariances, how these hyperparameters will change as you see more data when your model is a mismatch to the truth. But I can't remember the exact lessons from that. That's a good question. I don't have a good answer to that. I think it's important point, yeah.
You mentioned that it's important to try a few different values for the length scale. Would it make sense to use something like the minimum distance between 2 points and the maximum distance between 2 points and values in between those?
You mean for initialization?
Yeah.
Yeah, I think so. And in fact, we've discussed this a bit for GPy, if there are sensible initialization strategies we should put in. We haven't decided what they are. But things like that are sensible. I tell you one tip that I think you should do, that we should make more convenient to do in GPy, is to visualize the covariance matrix. So if you take your training data, and then you just compute your covariance matrix and then visualize it as a color plot, as we've been doing. At initialization, you really want to be wary of anything. I mean, say you're using stationary covariances. You want to be wary of anything that just has zeros off the diagonal. That's clearly a bad idea, because this is kind of what you're saying. You said, look at the distance between the data points, which is a really sensible thing, and set the length scale similar to that. So if your length scale is too small relative to the distance between data points, you will see a diagonally dominated covariance function. Conversely, if it's too big, you'll see that there's no structure in these parts here. It's just sort of flat. So you won't see a color variation of much. I mean, you should check, do the color bar beside, check that you know what the color variation is in those parts. What you really want at initialization, for each of your covariance functions somehow, is for there to be different structures, you know, that you're using in the sum in these off-diagonal parts. Then that means, what does that mean? That means that at initialization, you will get gradient sensitivity for the parameters of these covariance functions. If you have a diagonal dominance or something that's completely flat, and then you've added bias and you've added noise, then you know these covariance functions won't do anything. They'll just sit there not moving. So I think that's a practical tip that you should do in practice to help.
Can you use a global optimization to find hyperparameters instead of gradient descent?
We should do a workshop on that. Yeah, I think that this was, you know what I was thinking of, when I was thinking about giving this talk to today, I thought I should get Javier to do this. I mean, he's got optimization software, the GPyOpt, to do this optimization example. I think this would be a really great example, actually, for a global optimizer, because it's all two-dimensional, and you could actually use a global optimizer to see where you went. The surface is interesting, because it's got this ugly ridge up there. It doesn't look that much like a Gaussian process. So yeah, I think that's interesting. And I think my understanding, and you need to ask Mike Osborne this, but when Mike Osborne got into probabilistic numerics, I think my understanding is, I saw him talk first time about it. Mike Osborne was on the 10 o'clock news last night. Did anyone watch the news? He was interviewed on the 10 o'clock news last night, because he's got this work on predicting when machines will replace us all. It's next week, apparently. It was really cool. So, that's Mike. I was, my mum was there. That's Mike. Mum, that's Mike. I know him. But when Mike first spoke, the first time I saw Mike speak was actually about estimating integrals. And he's got a line of work in this that's been ongoing with other collaborators. And I think the integral he was trying to estimate by memory was the, if this surface here, if you exponentiate it and multiply it by a prior, is effectively the posterior. And you want to know the integral of that surface in order to estimate the marginal likelihood. And Mike's early work on that was estimating the integral of that surface. So absolutely, it should be possible to use global optimization. I think the reason perhaps you don't see it much in these type of cases is because this is rare. But I think it would be a fun example to put in as GPyOpt example to sort of show how, to see if we do actually get, because I think it may be a bit of a difficult example, I don't know. Well, no, it shouldn't be difficult. It should be all right. Okay.
You mentioned some fixed point update for estimating the signal-to-noise ratio parameter. Is it optimization algorithm?
Not the signal-to-noise ratio, the overall scale. So when you do this separation, and it's also quite widely used in statistics, if you do this separation, so you take, what you're basically saying is, in your likelihood, you're basically saying there's a scale times, there's your data minus a scale times f. In your likelihood, you're sort of pulling a parameter all the way out from the process. So you're saying, I'm going to fix my process to have a scale of 1, perhaps, and then I parameterize the underlying covariance to be in the form of a signal-to-noise ratio. So it's like a 1 minus alpha times k1 plus alpha times k2, where alpha is constrained to be between 0 and 1. Yeah? Once you've got that, you can now recover the full process by putting a scale on the outside. But that scale on the outside, or I should say that would be the scale squared, can just be interpreted as this parameter here. So actually, once you've got it in this shape, you can actually do a fixed point update for this because it's not hidden inside there. You can see what this parameter should be. And you can even put a prior over it. So you can even put a gamma prior over the square of this. And then you get what people call a T process. I don't really like the fact they call it a T process because it's a very uninteresting form of T process. They mean it's a student T process, but it's a very uninteresting form of T process because what tends to happen is this becomes very well determined after only like 12 points. Like you know what this scale is given your covariance function and 12 data points. It's really well determined because the posterior of that gamma over S squared scales, its degrees of freedom parameter scales with the number of data observations. So very quickly, the posterior of that parameter becomes a delta function. And in some sense, that means that the thing looks like a Gaussian process anyway. But there's a lot of papers making a bit of a fuss of that, but I think they're a bit misleading. Obviously, they're trying to sell the paper, so they sell the idea. It's very good if you've got very little data. So if you've got some examples where you've got very, very few data, and I think in matrix factorization, we did some work on matrix factorization with GPs, and I think that a way of improving that work would be to introduce that scale and put the prior over it. But it's a trick that's used in, so I think Jeremy Oakley would do it as standard for these Baco models, because why not do it, when you can do it? I mean, I've complained that it doesn't help much, so I still think it's a Gaussian process, but, it doesn't harm either. So I think that's a reasonable argument. So it works, but I think it's not as exciting as some papers make out. Other questions? So the challenges for GPs is they're n cubed. So this advantage of that they will keep learning from data as you add more training data also means they have to memorize the data. And in order to do the Koleski decomposition, you have to do an n cubed operation. And you have to store the covariance function, which is n squared. So they also don't deal well with discontinuities. We talked about how to parameterize a discontinuity, but I don't think parameterizing a discontinuity is very interesting. You want nonparametric discontinuities. So you want to know that discontinuities can happen at any time. If we knew when the Lehman Brothers crash was coming, and we could parameterize it as being there, then we would have all done things different. The point is you don't know when those sort of crashes or Russian debt defaults are occurring. They could occur at any moment. We could wake up tomorrow and there could be one, or it might not be tomorrow, it might be the next day, right? Those sort of large changes, Gaussian processes don't deal with them, not in a non-parametric way. You can say there's a large change here and there's a large change there and account for it with basis functions or whatever, but you can't do the idea, you can't marginalize over infinite potential large changes into the future, which would be nice. And then Nicolas mentioned this, this widely used, this is like the default covariance, exponential, quadratic, the RBF. It can be too smooth in practice for 1D, but there are lots and lots of different alternatives, so don't think that you're constrained to using that. Okay, so in the last half hour, I just want to sort of review a little bit the Kalman filter. Let's pause for questions there at that moment. And then what I'm going to do next is talk about the Kalman filter and go from the sort of representation of a Kalman filter to something that gives you the covariance function. And if there's time, I'll briefly wave my hands a bit and tell you how that allows you to do multi-output GPs. I'll connect that to multi-output GPs. The questions at that point? Okay. So this is a sort of a bit of a reset. Everything we've talked about so far, we're going to take a slightly different perspective. So Markov chains are another way. I mean, I think in general there's two tractable ways of doing probabilistic processes. One is Markov chains, or Markov property-based processes, and the other one's Gaussian processes. And the difference between the two is in the Gaussian process, you specify things by the mean function and the covariance function. We've been emphasizing the covariance function because the mean will just give you an offset, and that can be any function you like, deterministic. So we like the covariance function. That's what we've been focusing on here. A Markov process is defined by its initial probability and its transition probability. So you talk about a number of states that you're interested in, you talk about the position over the states, and you talk about an evolution process which gets you to a new state, etc., etc., etc. So the interesting thing is what happens if we make those two initial and transitions Gaussian. Because this is where you get the two coming together. So the Markov property would say that this is all the Laplace property, because he wrote it in his philosophical essays on probabilities, that the state of the universe at the next state is given by the state at the previous plus some evolution. And then if we say that evolution is Gaussian, so here this is a one-dimensional process, I've called it X because it's going to turn out to be a latent process in the Markov property, then what we can say is xi is Gaussian with mean of xi minus 1 and variance of alpha. You can make this more complex, we can do a lot, but it doesn't change the fundamental properties of the model to do so. And then you just need an initial state. And actually in what follows, I'm just going to set the variance of the initial state to be 0. So the initial state, I'm going to fix it to 0. So we need an initial state and then the following state, and now we've got a discrete time process that evolves as time moves on. And this is the thing, well, it's not this thing, this is a Markov chain, but this underpins the Kalman filter. So this is the sort of the nature of a process like this. So if you look at the numbers below, what I'm showing you is start at 0, x0 is 0, the noise epsilon 1 sampled from mean 0 variance 1 is minus 2.24. So x1 is just minus 2.24. And then similarly, epsilon 2 is 0.457, so you just pop back up a bit. And your current state is just the sum of the previous noise states. Yeah? So that is typically how we would define a Markov chain, and it's arguable that that's quite an intuitive definition. I'm not saying, what I don't want to say is that defining things as a covariance function is more intuitive than that. Maybe that's more intuitive, maybe not. But by going to a covariance function, we can actually integrate a process like this with all the other covariance functions we've talked about, because then the covariance functions just add to make the processes add. So the covariance function provides us with a language by which we can combine these processes together by addition. So what we'd like to do is find out what the covariance function of that process is. Now, we've already looked at this before. I've written it probably a different notation here. This is our formula for going between one process and another. And what we're going to do here is we want to go between the process for epsilon, what we're sampling for the noise process, and the process for x to give us the evolution of x over time. So that's the simplified version. That's the one we often use in practice. Now it's quite easy to see that the process we were talking about before has this form, that x1 is recovered because x0 was 0 by multiplying this vector by the vector of samples from epsilon. x2 is this vector because it's epsilon 1, which gives us x1 plus epsilon 2. And then so on and so forth. x5 is the sum of epsilon 1 to 5. So the relationship between x1 and epsilon is given by these equations. And therefore, we can rewrite the relationship between x and epsilon in this matrix form, where L1 I'm using to denote a matrix of lower triangular of 1s. So since x is linearly related to epsilon, then it's obvious that x is, which should have been obvious from the beginning because we only added things, but this makes it easy to compute the covariance function. We know that x is a Gaussian process, and we only need to compute the mean and covariance of, so I keep meaning to take that bit out. Okay, but this bit's perhaps interesting. No, let's leave it. Okay, we only need to know this, because I used to not teach at the beginning, the bit that I've just included there. I should take that out. This is the key formula. If x is L1 epsilon, and epsilon is a vector sample from this independent Gaussian normal, then we immediately know, if that's the scale of epsilon, that x itself is sampled from a Gaussian with 0 mean and this covariance. It's L1 transpose. Now, what I want to do is, this is a discrete time process. So each of these was at separate time intervals, but I want to talk about continuous processes. Discrete time is great, and indeed, the Kalman filter, as we talked about yesterday, was used to go to the moon, to track where the moon was versus the craft. And you can do that on discrete time. For signal processing, it's great. There's lots of advantages to it, but in these, for example, in microarray experiments, they often don't sample the cell at continuous time intervals. Discrete time intervals. They'll give you continuous time values. So you need models sometimes which are continuous time. So what we want to do is try and convert out what the continuous time process is, because that's what we typically work on. Now, to go from the discrete time to the continuous time, what you have to do is make the variance of the sort of evolution process dependent on the time interval. And when you think about it a little bit, the only thing that's consistent to do is to make that variance linearly dependent on the time interval. So if we sort of make, I could go through it sort of more formally, but if we had lots of little time intervals where each one of these is sort of delta epsilon, well, as you go forward, you should get the evolution of the process going as the sum of all these internal delta epsilons. So what you get actually is that the delta t times alpha for your variance. So if I make, so for example, if I ignore, going back to the original plot, it's probably easier to see. If at this point here, I want to ask the question about where should I be here, it's sum variance alpha twice. So it's 2 alpha, because that's the property of the Gaussian process. It's the sum of 2 Gaussian random variables. So that variance should be linear dependent on the time between observations. So all we have to do to make it a continuous process is include that dependence, sort of rewrite it in such a way that instead of having just a discrete thing, that we sort of say that the epsilon is sampled from the delta t. So now we're assuming we're seeing things at very small time intervals, alpha I. So if we half the time interval, we half the variance, so on and so forth. Yeah. So initially, this model here was delta t set to 1. And this is now our covariance. And it's the covariance of the same process, but we're just subdividing the times at which we observe that process. Now, what I want you to look at is this object here is the full covariance matrix, but the covariance between the ith point and the jth point is simply given by the inner product between the ith column of L and the jth column of L. So that's just the way you make up an inner product matrix. That's an inner product matrix, and these are the vectors that make it up. Now, the point about that is that the ith column of L contains sort of I zeros. Is that correct? I zeros before the ones start. And the jth column of L contains j zeros. So when you take the inner product between these two, you're just taking the inner product between a vector that's sort of 0, 0, 1, 1, 1, and another vector that might be 0, 1, 1, 1. So the sum of these things, so it contains I ones, doesn't it? Or, so when you take the inner product of these, all you're doing is you're counting the number of shared ones. So the value of the inner product of these can actually be replaced by the minimum of I and j, because it's just the overlap. Now, delta ti is your time interval. So now we can push through the delta t into the minimum, doesn't change the minimum, and then we know our covariance is of the form alpha min ti tj. So we have this odd-looking covariance function which says that the covariance between the 2 points is just the minimum of time I and time j. This is actually the covariance of Brownian motion. And it looks like this. It's a slightly odd covariance. At 0, because we've assumed the initial condition is 0, it's 0. And then all either side, because the minimum is 0. But as we go up, what we see is a linear increase. So along the diagonal here, it's time, basically. So the variance is increasing as time. So the actual standard deviation of the process is increasing as square root of time, which is a known property of a random walk of a Gaussian process. So it's something you immediately see from the marginal, from the covariance function, you can see that. That's hard to see from the initial and the transitions. So that's one property that makes the covariance function good. If we look at samples from this, that's what they look like. These sort of, it was Einstein that proposed the model of Brownian motion. So Brown sort of thought maybe the pollen things were alive or something. But Einstein, in fact, it's supposed to be the first, after Einstein proposed the model of Brownian motion, it was only at that point that people generally accepted that molecules existed. It was the first sort of macroscopic observation of molecules. I didn't quite realize that till I was reading up on it. So Einstein sort of proposed this model of Brownian motion that says that what's going on here is a particle is getting hit very rapidly by molecules, and that we can approximate those hits as sort of Gaussian random noise. That's the sort of stochastic differential equation interpretation of what's going on. So these paths are the sort of thing you get out of that, and it's related very much to the Markov chain. This is called the Gauss-Markov process, and it has this really interesting property that the conditional distributions, the conditional independencies of that process are such. Now, the precision matrix over Gaussian is the inverse of the covariance. It shows you the conditional structure of that graph. So we can build Gaussian graphs. We don't do it in Gaussian processes so much because they're not... Oh. Ooh, I stepped on something. Oh, came back. So what we really said in this case is that we've got, if people are familiar with graphical models, x1, x2, x3, x4. We specified conditional distributions, so we're linking things in a chain. That's why it's called a Markov chain. That structure gives us the conditional independencies. So x1 is conditionally independent of x2 given x3 given x2. You can always visualize that conditional independence structure by looking at the precision matrix of the Gaussian. So this is the inverse, or the precision, the inverse covariance, or the precision matrix. And it's 0 of these things. Now the cool thing about this is that I just took the inverse of that to create that. And you'll see, I mean, you can try this yourselves. It's one of those weird, oh wow. But you basically get this conditional independent structure popping out. It doesn't work in continuous spaces in more than one dimension, because what a conditional independence is in a continuous space is a bit hard. Well, I don't kind of know how to make that work, but it works in 1D. And what you're seeing is this triangular structure that says that each point is dependent. What these blues, these off diagonals show is that the conditional independent structure for x2 is it's only dependent on x1 and x3. The non-zero terms show you that. So these are called partial correlations sometimes as well. It's sometimes called the partial correlation matrix. But it's the result of specifying, and if you start specifying things like this, you would see in the inverse covariance off-diagonal terms associated with each edge. Sometimes, if you normalize that, it's sometimes called the graph Laplacian, but we don't normalize that normally in the GP because it makes the matrix non-full rank. And it's actually, in many senses, it's a different type of model. I'm not going to go into the details of that now because I'll move on that, but you can ask me about that a little bit in the break, about how models like this, Gaussian random fields, we would talk about these, how they relate to Gaussian processes, because they're not valid covariance functions. I have an explanation of what they are. I won't go into it now. Now, if you do the same thing with this exponential quadratic, this color map really, whose eyes are freaked out by that, apart from, yeah. So you must be colorblind like me, yeah. So are you colorblind? No, you are now. There's two. So it's funny, I was waiting for Javier to say yes, because he told me he was colorblind last night. My eyes are totally freaked out by that plot. These bands are really, ooh. But what you see here, this is the precision matrix of that exponentiated quadratic. Now you're still seeing it's dominated by those neighbors, those nearby terms. But look, the terms go out. In fact, in theory, numerically they drop to 0 after some point. But in theory, they go out forever. That's the infinite Markov property of that exponentiated quadratic. So it's a very different property from what we're seeing in this example, yeah? Where my eyes aren't freaked out by that at all. So there's the two together. You also get these edge effects. Ignore them. Just look at what's going on in the middle, and you just see these additional correlations coming in, which is showing that there's somehow, for that one, there's correlations going all over time, right, like this. You can't represent it by this. Oh, I drew one twice there. Sorry. You can't represent it by that simple chain. Everything's interconnected.
I'm a bit confused. Didn't we have the property for the covariance matrices that we can add additional points, and the other ones will be unchanged? Here it seems if we add an additional point, then like in between 2 points, then the ones which were neighboring before should be independent now if there's
No, because you're thinking of the precision matrix. That's
Oh yeah.
absolutely correct. You've just made exactly the point why these are difficult models to work with as a process. So the point was made there that, yeah, if I now add a point to this precision matrix, then the elements will change, because if I add an observation between these 2 points here, that's very well explained, because I wasn't going to explain this, but that's an excellent explanation. If I add a point between these 2 points here, then these 2 things will zero out, and I'll gain 2 new elements. Because by inserting an observation inside between these 2, I now make the conditional independencies appear here. So I gain an observation. I change the structure globally of the precision matrix. It's a global change in structure for the precision matrix. But it's not a global change in structure for the covariance matrix. That one's fine. So adding a point here only adds a row and a column, doesn't affect anything globally. And that's why the covariance is the right representation for processes. Because if you try and do it in the precision matrix, it basically causes effects everywhere. So that, so it didn't seem when I first did that, oh, we can look at the marginal distribution, zoom down here. You can't do that for the precision matrix. If you look at the marginal distribution for this, it's not related. We can't just sort of say, throw away all those and zoom down to here. We need to look at the marginal either side. If we were trying to marginalize out these intermediate points, we would have to add elements to this covariance matrix which precision matrix, which don't exist in the first place. So that's why you can't express processes in this sort of connected way. They're not valid prior processes. They're valid probabilistic models over a discrete number of points. They're not valid prior processes. Okay, so in the last 5 minutes there, I'll just rush through this sort of how we extend that Markov chain, because that Markov chain is not a Kalman filter. In Kalman filters, you tend to have processes evolving state variables, which you may evolve in more interesting ways than what we're talking about. I've just said a chain moving along, varying. And we can imagine 5 or 6 of those independently varying together. In a Kalman filter, you probably wouldn't have them independent. But you can vary that part. But I'm just going to assume that we've got some latent state, like we had in the latent variable models yesterday, of evolving independent chains moving in time. And that's my distribution over them. So this matrix here has n rows and q columns. And then I'm saying it's independent processes across each of those things, a bit like we did yesterday for PCA. And that's the covariance function of each of those processes. Now what I want to do is I want to attain, in a Kalman filter, is I look at those independent processes and I say, I don't observe those, I observe an affine transformation of them. This is just like PCA. So in PCA, that's what we did. We say we've got some latent thing going on, and I multiply it by W to observe things in the output. But the complication here is, in PCA, we assumed that this was independent over time. So basically, this is expressing correlation in the columns, and this is expressing saying mix the rows together. So these two things are operating in different directions. So it's not quite simple. But this is, once you understand this, you can do all Tucker methods, everything. It all follows from this idea, is that you can actually express this with a stacked system, a Kronecker decomposition. So Kronecker products, so you'll see this and it looks complicated, but all it's doing is rewriting things such that you get a vector back. So instead of X being a matrix, what I'm taking is, I'm assuming that I'm redefining this matrix X as a vector where each column of matrix X is stacked on top of each other. So I bring these all down to give me a vector. And now I'm going to talk about correlations across this entire thing. Now what's that mean I'm doing? I'm starting to talk about correlations. I don't want to talk about Gaussian distributions over matrices. That's a broken way of thinking in some sense. Sometimes it's convenient, but the most general thing I can do is talk about correlations between time point 2 of this process and time point 7 of this process. I want to include all these sort of ideas. Correlations for everything. What's the correlation between the amount of rainfall yesterday here and the price of sushi in Vancouver? Probably nothing. But in theory, you could specify that. Those are different functions at different times, potentially. You should be able to specify that. And in a Gaussian process, that's sort of what you want to do. Correlations over everything. So the way to do that, first of all, is to turn those separate functions into a single function. So now in this single function, you've got like 4 different processes going on. But within that function, there's a load of independencies. So they're really separate functions. But this is a more general expression. So we start by doing that, and now we have this vector of what those latent processes were. And that is the Kronecker product. So the Kronecker product is defined like this. If I take the Kronecker product between two matrices, it just gives me a tiling, a scaled tiling of the matrix. So I cross k, as I had here, just gives me k down the diagonal with zeros off diagonal. So I've got those independencies I want. I like to sometimes visualize it with colors, so I'm trying to say, well, even though I'm colorblind, that's why I like the tiling idea, right? It's a scaled tiling, yeah? So it's just tiling matrices. It's just a mathematical. I think did Einstein have to do this for general relativity? Makes it sound complicated, but it's not that complicated. It's just like other linear algebra. Once you get used to it, the rules are simple. So what I'm trying to visualize here is that tiling of the Brownian motion that comes from the Markov chains in the latent space. And now I'm trying to scale that up by the matrix, the identity matrix, giving me this tiling repeated with zeros in the off diagonal. So that's my process. This is my function, which is actually 3 functions, or 5 functions, or 10 functions. But I can write it as I cross k. I Kronecker k, I should say. I say cross because that notation we use, but I don't think that's standard. I Kronecker k. So this is the interesting, because now this is a stacking, but there's 2 stackings. What happens if we stack the rows like that? So we stack the columns here, but we could stack the rows. So take the transpose and stack. So I always think of stacking columns, so let's call it transpose and then stack. So in this stacking, what it's given us is the marginal distributions are in blocks. But if we do the other stacking, so that's the marginal distribution of one process. If we do the other stacking, so if we do a row stacking, we just have to flip these Kroneckers around. So it's k cross I, if we do the other stacking. And in that case, we get something that looks like that. Now the marginal distribution in this block here is the one across the independent processes in the latent space. Yeah? So the point about this is that's the thing we want to multiply by W, the marginal across the vector in the latent space. So the complication I'm trying to get around by introducing Kroneckers is we're not multiplying. When we use the Kalman filter, I mean, you can do whatever you like, but in the way I'm introducing the Kalman filter, we don't multiply the entire time series of one of these things by the matrix W. We're trying to multiply the different independent dimensions. And by Kronecker stacking in the other way, we get that representation out. So it looks like that. And now, if I Kronecker stack by rows, which is not normally how I would think of doing it, my default way, so I'd say Kronecker stack the transpose. Sorry, Kronecker stack, just stack the transpose, Kronecker stack, blah, blah, blah. Then this is now my covariance function. So this is k cross I. Now, the reason for all that effort is now I have the marginal distribution of those 3 latent processes at time 0. Yeah? And now I can start applying these rules. Once I've introduced those Kronecker products, I can apply these rules. If the observation, the high-dimensional observation of the Kalman filter, multivariate observation at time I, is given by the latent process at time I, multiplied by W, plus some, I don't know, this is called the emission distribution. So typically in a Kalman filter, you would do this in a more complicated way, and every time you wrote down a matrix, you'd give it a name as if you'd just given birth. That seems to be the way it goes. But I don't like doing that because it confuses everything, so we can just keep it in this sort of simple way. So this is the sort of emission, this is defining the relation between the latent variables and the observations. Now, if we've horizontal stacked, doing that to each time series at a time is equivalent to W, which would be I Kronecker W, times the sort of row stacked version of the matrix, which would give us all these. So this we could write now, Y is equal to this times this. So that allows us, so I've skipped a step there, haven't I? So that allows us to, in effect, write that, so let me write that in Kronecker terms. Our actual observation for the stacked version of Y is equal to I Kronecker W times X, where that's the stacked version of X, plus epsilon, which is an enormous noise vector across everything. If we do that, And then we sort of say now x is given, if we horizontal stack x, the covariance for x is drawn from a Gaussian with zero mean and k Kronecker I stacking if we've horizontal stacked it. We can do everything the other way around. We can say if we column stack, this is w Kronecker I, x plus epsilon, and x would be I Kronecker k. But you just see that the I and the k are in the opposite position. So when you do the next part, which is to sort of say, well, the result of doing this in general, if this was A and this was sigma, would be a covariance matrix with A, sigma, A transpose. We apply that rule, and we get the covariance of the new thing is I Kronecker W, K Kronecker I Kronecker W transpose. Rules of Kronecker products tell us that this is how you do the products, that the products just fall through. So this thing here can be rewritten as K Kronecker W transpose. And so what this is doing is taking a K matrix, which is your covariance over time, and then tiling it by a matrix W transpose. Now typically, we'll often refer to this matrix as B. So W is a factorization of some matrix B. In the Kalman filter case, that's a low rank matrix B. But in general, this could be anything. And I think one really interesting case, it can be like a graph Laplacian. We haven't implemented that in GPy. This is implemented in GPy, though. Plus I sigma squared. So this is giving you multiple outputs. And what this is telling you is the correlation matrix between your outputs. And so these models were initially described in sort of geostatistics. And in geostatistics, they're called co-regionalization models, and that the matrix of W transpose is called B, and that's called the co-regionalization matrix. So Maurizio, who's here, so he's the sort of expert, did a load of work, and I put my name on the end of the paper, to find out how all these things interrelate and described sort of how different kernel methods work. With Lorenzo Rosasco, who's sort of a kernel methods guy who worked on multitask kernels, trying to sort of give an overriding view of geostatistics, kernel methods, and the Gaussian process perspective on these, which is sometimes called multitask learning for GPs. I'm not so keen on that name myself. And this paper here, Maurizio did an amazing job of digging out all the different references and so on and so forth. And what they, in effect, they allow, this is sometimes it's written in this way, that if you want to do, so sometimes people say, well, what this really is a kernel that spits out a matrix given x and x prime. The matrix in the case we're talking about would be B times kx x prime. That's the thing we're talking about, the co-regionalization structure. I'm out of time, so I just sort of write it like that. And then the sort of thing that the paper talks about is how you can start combining these things. You can go wild with this stuff. This is actually a really powerful framework. Our initial premise, Maurizio's PhD, was actually about very interesting convolved multiple output Gaussian processes based on differential equations. We're not going to talk about that. You can read his papers on that. And the reason we started investigating these models is because we're like, we'll be able to beat these models easily because they're way simpler. And then, unfortunately, Maurizio was a very good student and tried very hard to get these models working and showed that these models are really powerful. So, because you can, the original model is not so great itself, but you can start adding them together. So you can start having these different co-regionalization matrices over different kernel structures. So just as you can weight your kernel matrices individually, you can start weighting by co-regionalization matrices. And these things get super complex. You can certainly start overfitting with these models. In fact, there's an example, I can't remember if it's in the lab, but there's an example online of a notebook I did where what we try and do, this is a fun example, you try and co-regionalize. So you take the 100 meters, 200 meters, 400 meters, men and women across Olympics from 1896. But men started running 100 meters in 1896 and 400 meters, I don't know, in 1920 or something, but women only started in 1964. So you're trying to reverse interpolate, look at co-regionalization to predict backwards in time. And you can try different structures of the co-regionalization matrix, and you get some serious overfitting, and you get some serious incorrect extrapolation. So you can really, they're quite powerful and can do quite a lot of stuff. You may need a lot of data to describe them. Just to sort of show you, give you a brief hint, these are some different structures that are end of the talk, but the structure, so some of these are quite obvious that they're interrelated. So this one is a rank 1 co-regionalization matrix multiplied by a standard kernel matrix. And this one here, in effect, is just one process is a scaled version of the other, right? because there's only one latent process, that's rank 1, and then you're just scaling them up in 2 different ways. And that's what the kernel looks like. This one here is a little bit more complicated because this is a full rank process. So there's 2 latent processes being combined together, but they both have the same underlying covariance function. That's key. So you see one covariance function here, but there's 2, but they've got the same length scale. And that's not super complicated either. This is the Kalman filter case. The thing you can't do with Kalman filters is now something a bit more interesting. If you add 2 Kalman filters together, you only get a Kalman filter back, because adding 2 Gauss-Markov processes just gives you another Gauss-Markov process. If you add 2 general covariance functions together with different length scales, you get the effects that Nicolas was showing us yesterday. So each of those effects he was talking about, with the long length scale, the short length scale, the periodic, can now be co-regionalized in different ways across different outputs. And that's the more complicated sort of model that now follows. So this is actually, that's an example of it. So this is sort of one short length scale process being co-regionalized in this way, and a longer length scale process being co-regionalized in this way. And you can keep on adding those things together. You know, it's not necessarily clear that these are correlated processes. And they've got quite a lot of parameters in, so you can see it gets a bit dangerous. Okay, so there's various ways these have been used in machine learning and stats, including there was a semi-parametric latent factor model, which was worked by Yi Tay and Matthias Zager, which is a special case of this. It's where there's where B is rank 1. That's kind of what it looks like in practice. And there's also work by Edwin Bonilla and Chris Williams, and I can't remember the other author, on the intrinsic co-regionalization model, is called in geostatistics, as an approach to multitask learning. And I think that's it. Okay, so at the time that we were talking about these, there was also a lot of interest in these the computer models that I talked about at the beginning, where you've got multiple predictions coming from the computer models, co-regionalizing those. So that's another area of interest for that. So I've overrun a little bit, but if there's a brief question.
Yeah, sorry, well, one question that kind of follows into another question. So when you take a tensor product structure for covariance measures, you assume a single correlation between the 2 tasks, independent of where they are in the input space.
Not for the intrinsic co-regionalization model, yes, but not for the not for these things. So for these things, this is weighted by where things are relatively in the input space. So depending on, so you get one correlation if this thing's firing. You get a sort of weighted sum of correlations depending on the relationship between X and X. So it can get quite complicated.
But I mean, blockwise diagonal, the B's, B1, B2 are still going to be constant depending on the difference between tasks.
That's one way you can specify it. You can specify them, of course. There's lots of ways you can specify B, but yeah, that's a standard way.
So if you don't want them to be constant, do you have to then force those into your covariance structures, into your Ks? I mean, is it a computational reason for people?
If you start doing these summing together, you lose the computational advantage of this. And the work Maurizio and I were doing was linear operators on these kernels, so convolutions, which effectively do what you're suggesting. So you merge stuff in. But another thing you can do as well is you can make, and this is what Nicolas effectively mentioned, this is a way of constructing covariances, is this could be a covariance over time, and this could be a covariance over space. So there's just because all this is just multiplying of covariances together. That's a fixed covariance of a Gaussian distribution. So you're saying I've got a fixed number of outputs, and this is a Gaussian covariance function. But you could always replace that Gaussian distribution with a process itself. So if you had some knowledge about how you expected those things to vary, you can include it in this structure and effectively constrain what these B's are and say they're varying over space.
So you get like a natural blockwise structure, but you lose the fact that because the tensors you can't just invert them down.
Yeah, but you can't invert. Annoyingly, you can't. So there's some. I had a paper with Ollie Stegon, and they did a follow-up, which is even more advanced, about what sort of structures like this you can invert efficiently. So sorry, I should have mentioned this earlier. This structure you can invert efficiently, because the inverse of this is just B inverse K inverse. But when you add them together, you can't do that. What you can do is you can start playing tricks with doing the eigen decomposition, but they get a little bit more complicated. So as you start doing lots and lots of sums, I don't think there's a general way of doing that efficiently. Certainly, you end up just having to invert the whole thing. So that's a good point. A big problem with these methods is if this is m outputs and n data points, you basically increase the size of your covariance matrix, worst case, to mn. So now you're m cubed, n cubed, or m squared, n squared in terms of complexity. So there's even more call for approximation methods. James is going to talk about them later on. But yeah, and this structure doesn't allow you to sort of, the general structure of the linear model of co-regionalization, which is the most general thing, doesn't allow you to invert efficiently. The intrinsic co-regionalization model does. And that's why it's quite widely used. Other questions? Okay, great. So have we got the coffee? Break for coffee? So I've overrun a bit. Start again at 11.